You want to build a lightning-fast manufacturing robot, right? You picture it just zipping around a factory floor, totally flawless. But if you miscalculate the physical limits of your gears, well, that beautiful machine will literally tear itself apart.
Yeah, the moment it powers on.
Exactly. Welcome to this deep dive. Today we are taking a stack of R&D and manufacturing notes and decoding the hidden physical laws of precision transmission.
Because, you can't push a machine to the edge if you don't actually understand where that edge is.
Right. And according to the notes, every system needs a baseline.
It does. In mechanical engineering, we look at rated torque first.
Okay, let's unpack this. Is that like the top speed?
No, not quite. It's the maximum average output load a gear system can handle continuously, like to guarantee its design life, which is usually around 10,000 hours.
Wow, 10,000 hours is a lot of constant movement.
It really is. So if you're designing a robotic waist axis, the everyday continuous lifting and turning has to stay under this limit. Otherwise, the metal just fatigues and fails prematurely.
So rated torque is essentially a runner's sustainable marathon pace.
Yeah, that is a great analogy.
But a marathon pace doesn't account for, say, sprinting off the starting line. I mean, overcoming inertia to get a heavy robot arm moving from a dead stop requires a massive sudden burst of energy.
Oh, absolutely. And that is where repeated peak torque comes in. This is the absolute maximum force allowed during startup or stopping.
Because the physics there must be pretty brutal, right?
Very brutal. Getting a static mass moving puts immense shear stress on the gear teeth.
Oh, I bet.
So in the field, you have to strictly program the motor's acceleration profile. If you don't keep it within that repeated peak limit, the teeth will literally shear right off. You are effectively throttling how fast the motor ramps up just to protect the internal mechanics.
Okay, so we limit the acceleration to protect the gears from snapping. But what about sheer velocity? The sources highlight permissible input speed.
Yes, and they note that exceeding it causes rapid heating.
Wait, why is speed generating so much internal heat?
Well, think about what is happening inside a harmonic drive. That's a specialized high-precision gearbox we use heavily in robotics.
Okay, I'm picturing it.
You have an elliptical component called a wave generator, and it's spinning incredibly fast. It's constantly stretching a flexible metal cup, which we call a flex spline.
Stretching metal at high speed sounds like a recipe for intense friction.
It is. And at a certain rotational speed, that friction simply overcomes the lubricant's ability to cool the system down.
Oh, so the oil just gives out.
Literally shears and breaks down. The metal overheats, expands, and completely destroys the bearings.
That is wild. So high-speed scanning applications really have to track that thermal boundary.
Very carefully, yeah, to avoid melting down.
But speed introduces an even worse scenario.
Right.
A crash. The deck mentions emergency stop torque.
Right, that is the structural shock a system can take during a collision without the gearbox housing basically exploding.
Okay, but let me push back on that. If the housing holds together and the robot survives the crash, can you just, hit the reset button and trust it?
Well, what's fascinating here is that you would think an intact housing means an intact machine.
Yeah.
But the kinetic energy of a crash doesn't just vanish.
It goes straight into the internal gears.
Exactly. The housing might look fine, but those tiny flex spline teeth are often permanently deformed.
Just from one sudden stop.
Yeah, even by just a few microns. And since they require microscopic alignment to actually function, you almost always have to completely recalibrate.
Or even rebuild the whole joint.
Often, yes, because that sub-millimeter precision is completely gone.
That puts engineers in a really tough spot. I mean, high torque snaps teeth, high speed melts lubricants, and crashes ruin alignment. Yet modern assembly lines move at terrifying speeds.
Well, they do.
How do they physically achieve that without hitting all these limits?
So they manipulate mass. Specifically, they focus on the moment of inertia, or J.
That's the equivalent rotational inertia of the system.
Right, from the input side.
Mm-hmm.
If you have less mass resisting rotation, you need far less torque to get it moving and less time to stop it.
So what does this all mean for the big picture?
It means using a lightweight series minimizes inertia. That is exactly how a Delta robot, those spider-looking arms sorting things on a conveyor belt, can hit a blistering 200 picks per minute.
200 a minute.
Yeah, they use ultra-lightweight materials in high-frequency servo systems, so the motors aren't fighting heavy metal.
Less rotational inertia means a faster dynamic response and less energy wasted just fighting the machine's own weight.
Exactly. Designing these robotic systems is a really delicate physical dance. You are managing torque for longevity, watching thermal speed limits, and minimizing inertia.
Which leaves us with a really compelling structural paradox to think about. Engineers are constantly utilizing lighter materials, right?
Right, to minimize that moment of inertia for faster speeds.
Exactly. But how do those same lightweight materials handle the massive, sudden forces of an emergency stop torque during a crash?
That is a fascinating structural trade-off.
It really is a constant battle between the need for speed and the need for survival. Definitely a puzzle for you to explore next time you see a machine blurring past.